Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video. Hopefully by the end of it, you'll be able to use what we've learned about independent events to calculate the probability of compound events. So compound events are events where more than one thing is happening, like a multi-stage event. So we know that the probability of A and B is just the product of their respective probabilities. That's if the two events are independent. Remember, this comes about from the conditional probability formula. We also know from a previous lesson that the probability of A or B is just the sum of the respective probabilities, and that's if the events are mutually exclusive. So let's use this to find the probability of a compound event. So let's have a go at this question here. So what we have is we have a group of 7 Year 11 students and 4 Year 10 students. We're going to give out 2 prizes. We want to find the probability that one but not both prizes go to a student from Year 11. Now the answer to this will depend on whether or not the same student can win both prizes. So let's have a go at first if the same student cannot win both prizes. So what we're essentially saying here is we only want one student to be from Year 11. So we're finding the probability that the first student is from Year 11 and the second student is from Year 10, or the first student from Year 10 and the second student from Year 11. That's essentially what we're finding here. So because these are mutually exclusive, you can't have both of these happen. You can't have the first student being from Year 11 and from Year 10. We can just find the probabilities of each of these and add them. That's using this rule up here. Now to do that, we're going to use independent events. So the probability that the first student is from Year 11, well, there are 7 Year 11 students and there are 7 plus 4, 11 in total. So that would be 7 over 11. Now, what would be the probability that the second student is from Year 10, given that the first student is from Year 11? Well, if the same student cannot win both prizes, that means after the first Year 11 student wins a prize, there's 10 more to choose from, and there are 4 of those are in Year 10. So this is the probability the second student's from Year 10, given that the first was from Year 11. So something similar would happen over here. The probability that the first student was from Year 10, 4 to choose from out of 11 in total. If the first student was from Year 10, then there will be 7 Year 11s left over and only 10 to choose from, because this Year 10 student who won the first prize cannot win the second. So I can simply put that in my calculator. And what I get is 28 over 55, so just over 50%. Now, I would get a different answer if the same student could win both prizes. So over here, I'd be calculating the same thing. Either, because I only want one of the students from Year 11, either the first student is from Year 11 or the second student is from Year 11. So I'm going to do exactly what I did last time. I'm going to calculate probability the first student's from Year 11 and add that to the probability that the second student is from Year 11. This time, the numbers will be only very slightly different. So this time, the probability the first student's from Year 11 is still 7 over 11, but the probability that the second student is from Year 10, this time will be 4 over 11. There's still 4 Year 10s to choose from, but I have 11 students in total, because this student that won the first prize can be picked again. So that's why there are 11 choices. And similarly over here, probability of a Year 10, then a Year 11 looks like this. So the answer I get will actually be 56 over 121. So this time it's a little less than a 50% chance. So both of these were compound events because they occurred in stages. There was a first prize given out, then a second prize given out, and we used both of these rules as well as what we know about conditional probability in order to solve them. How awesome is that? Now, I should point out that either of these questions could have been solved using a tree diagram. We'll do tree diagrams in a subsequent lesson. I just want you to have the option of doing it without a tree diagram or with a tree diagram, whichever one you please. So now we're going to do a question that's slightly harder. So let's look at this question here. We know Queensland and New South Wales play 3-match State of Origin series, and the winner of the series must win at least two or three of the matches. So we're going to assume here that the outcome of each match is independent of other matches. So that means the outcome of the first match doesn't affect the chances of each team winning the second match, and so on. So let's say Queensland wins each match with probability 0.55. What is the probability they win the series given that they win the first match? So in order for Queensland to win the series, they need to have either won all 3 matches or they need to have won exactly 2 matches. So because those 2 events are mutually exclusive, I can add together their probabilities. So what we're saying is the probability that Queensland win all 3 matches, given that they win the first match, plus the probability that they win exactly 2 matches, given that they win the first match. So again, I can add these up because I'm finding the probability this or this happens, and these 2 are mutually exclusive. Queensland can't win all 3 matches and then win only 2 matches at the same time. So let's figure out these 2 probabilities. So let's start with this first one. What is the probability they win all 3 given that they've won the first? So the probability that they win all 3 and the first is just 0.55 to the power of 3. Because they're independent, the probability that Queensland win is 0.55 times 0.55 times 0.55. So we put that over the probability they won the first match, which is 0.55. So what we've done here, the probability of this and this over the probability of this. This comes just from the conditional probability formula. So for this second one here, the probability they win 2, given that they win the first. So we have to find the probability they win 2 and they win the first. So the probability that they win 2 and win the first. So we could have them win the first 2 and then lose, or we could have them win the first and the third. So the probability that they win the first and end up winning 2 matches, so the probability of each of this first one is 0.55, that's the first win, times 0.55 for the second win, and the probability that they lose is 0.45. 0.55 times 0.55 times 0.45. But then in the second one, it's actually going to be the same. It's going to be 0.55 times 0.45 times 0.55. It's going to be this same number here. So we can just times that by 2. This tells us the probability that either this happens or this happens. Because these 2 have the same probability, we can just times this probability by 2. So the probability of winning the first is again 0.55. So we use the conditional probability formula. Probability of this and this over the probability of this. So putting this all on our calculator is equal to 0.7975. So that's the final answer. There's almost an 80% chance they'll win the series if they win the first game. So another way you could have thought about this is you could have said, okay, they've won the first game. So for them to win the series, they can either win the next 2 games, they can either win the second and then lose the third, or they can lose the second and win the third. Each of these events would result in them winning the series. Here they would have won all 3 games, because remember, we know they won the first. This would be 2 wins and 2 wins. So using independent events, this would just be 0.55 squared. Over here, the probability they win times the probability that they lose and then this would be the probability they lose times the probability they win. I can times in each of these due to independence. I would get exactly the same answer. Whichever way you do it doesn't matter. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.